Sure. You ready?
Sure.
Okay. Okay, my pleasure today to introduce our speaker, Patrick Cavanagh. I've known Patrick, I guess, I think we figured almost 3 decades now. I visited Patrick when he was at Harvard University, and as I mentioned, I was super impressed with just the way his lab was set up, very communal, and all of his students working together, which was really beautiful. Patrick has a Bachelor of Engineering, we won't hold it against him, from McGill University, and a Master's and a PhD in Psychology from Carnegie Mellon. He's actually a double emeritus, so emeritus squared.
Squared emeritus.
He's emeritus from Harvard, where he did most of his work, and then he moved to the University of Paris, and he's emeritus from the University of Paris as well. In Paris, he set up the Vision Attention Lab, and at Harvard, he worked with Ken Nakayama and ran a joint lab together. From Paris, he moved to York University, and he's at Glendon College in York University. He's graduated 30 PhDs and supervised 39 postdoctoral fellows. And, the CV goes on and on, many, many, many papers. I think the thing I like most about Patrick's work is it's psychophysically very rigorous. The experiments are all elegant. And, highest accolade I give is his papers are all well written. They're easy to digest. It's not a super hard job to get the elegance and the rigor that's in his work. So I hope everybody appreciates the work that Patrick's going to present today, and give him a warm welcome.
Wow, you're way up there. Wow. Everyone can hear me okay?
Yes.
Okay. Well, we're going to take a little tour through position. So most of you know this brain and know the difference between the what and the where. So I'm going to be a little bit on the where side today. So much of the research in vision and in all of the senses is in what. Like what are we seeing, what are we hearing? And the recognition pathways are pretty well mapped out and understood, and receptive fields and face receptive fields and so on. There's a lot of very exciting, interesting work there. On the other hand, for position, it's not so well mapped out. So we're going to see what we can do about clarifying the issues here. Now, you may think, well, position is just what objects have. It's not so important. But really, here's an example. As these things flash on the screen, and as you probably have noticed in real life anyways, you can often have things that appear briefly and go away, or you look at them briefly and then look somewhere else. And you can tell where they were, but you can't tell what they were. So that's the kind of like where comes first. Don't forget that. That's the important part. So any object that you experience, you see, has a position first and an identity second. So how does that position part work? That's what we're interested in. Now here's those things you were looking at. Some of you may have noticed, but some may not. Okay, well, it's not the case that we know nothing about position. There's a whole area basically in rodent work on how do we know where things are around us, or how does the mouse or the rat know where things are around them. And very exciting work on sort of place cells. You probably know lots about place cells, where they are, or grid cells, where things are inside a landscape. And it is true that the input to those navigation systems, most of which seem to be around the hippocampus, come from vision, landmarks and so on. But the question today is not that. It's not how do I know where the screen is behind me, or I really don't know what's behind me at the moment, but I might have if I'd taken a look. How do I know about things that are behind me or around me, or how do I get out the front door in this building? This is about how do you know what's right in front of you, what you're looking at right now? What is it that tells you where something is, where I am in your visual field? Now, you might think that's pretty well understood, because we do know that every visual cell has a receptive field, and every receptive field is characterized by a location in space on your retina, whereabouts in space that part of your retina picks up. And so a cell here that you're recording from will respond to stimuli within a small area of the visual field in front of it, but nowhere else. So doesn't that really tell you where locations are? If each cell has a coded location, that seems to be the answer. Not only that, but the cells are arranged in this kind of nice cartoony version in a retinotopic fashion. So one cell has a receptor field here, the cell beside it has a receptor field a little bit further over. And they make these nice maps. So aren't maps and receptor field, isn't that it? Isn't that the code? Well, we'll look at a few things that say that no, that's not the code, although it's the data, it's the basic data. But in fact, our experience of position is not simply what's on the retina, corrected for the direction of the eye. And I'll give you two arguments for it. Oh, here we go, whoa. First one is a 100 millisecond delay, and the second part of that is that, well, things are moving. Think about things that are moving. So as you all know, the information that lands on the retina or in the ear or on the skin has a certain delay before it arrives in awareness. Maybe a tenth of a second. That's maybe a bit fast, but somewhere around there. So what happens then when things are moving? In other words, take a look at, this is Nadal, right? How do I get over here? Where's that? That's not there. Is it there? No. I'll find him. Hang on. There he is. Okay. So this is Rafael Nadal, and he's going to hit a ball. And everybody knows you're supposed to look at the ball, but he's really pretty good at it. Okay. Now, watch his eyes. Where's the little thing? There he is over there. Let's go back here. Whoa, whoa, whoa. Hang on. There. Look at his eyes and the ball. Okay, so just think about that for a second. His eyes are directly at the ball, but he cannot possibly be having any awareness of that ball. The only awareness he can have is of a ball a tenth of a second ago. Well, a tenth of a second ago when it's traveling 30 meters a second is way over here. So this ball over here has enough information in terms of velocity, direction, who knows what, for his eyes to have predicted where it will be exactly at the moments in front of his face and to get there. So his action has made the prediction of the present. So the action predicts the present based on the motion information he got from the ball over here. And we believe his perception does the same, that he's not actually looking at blank space. His experience is not of the blank space that his eyes would be picking up in terms of the input at that moment, but in terms of a prediction from a tenth of a second ago of a ball in front of him. Maybe at the wrong angle, but still, he's predicting the present and seeing that. So this is aspect saying that it's not what's registered in terms of receptive fields that determine how we perceive position. There's a lot more going on to it. It's a construction, and we're going to look at how that construction might happen. Okay, so who cares about perception of position anyways? Or who uses position? Oh, action, of course, as we saw in that example. But also, of course, vision, where are things? Audition as well, where are things in the world around us? And touch, where are those things? But also attention. So we'll come back to this later, but attention in particular has to know where the input is, because attention is going to come back down as a projection to boost this information here, right? That's attention's role. Let's select and boost the information of the target. Okay, but there's a delay between registering that that's my target and then sending this down. And in that time, this truck has moved. So attention has to be able to target the location of the stimulus by the time the attention gets to it. Okay, so attention needs to have information about position as well. Okay, so that's the idea. So position is something you construct. You build a story about where things are. And of course, it's based on this retinal input, where the receptor fields and so on are giving you, what the information they give you. But it's more than that. So here's an example from color constancy, where you know that this square here, this bit here, and this bit here are exactly the same. Do I have the two right ones? I think so. No, this one, we'll, we'll have to find out. Hang on. The top one and the bottom one. Okay, let's go back there. Okay, so which one was it? This one? I don't know if I can remember.
Two little arrows.
This one and that one? Okay, yeah, they don't look alike now anymore, do they? It's hard to find. But those two, in fact, have the same light coming to your eye from the screen. And what you've done, of course, is you've taken into account the seeming reddish illumination and the greenish here, so that they look very different. You've discounted the illumination, when in fact they're the same. Now, we do that a lot, discounting things. You know, if you do social psychology, you discount intentions to get, discount context, sorry, to get intentions, and so on. What we're going to do today is look at how you get to position by discounting things like motion. You saw that example with the tennis ball. So discount an object's motion to predict where it is now. And the second part is coding positions relative to their backgrounds of frames. So how is it that position is constructed? Well, there are probably a lot of things we could look at. We're going to look at this question of motion. The motion clearly is changing where we see things, and maybe we can track down how position works by following the effect of motion. And then there's even a higher level point about how you see the world around you in terms of frameworks. You know, the screen, me down here on the desk, what's on your lap in front of you, these different frameworks, and each position of an object is kind of based in that frame. So we'll come back and see how that works near the end. And of course, our goal is to say, well, what is position after all? How does it work, and where is it coded? How does the brain do this? Interestingly, to get to an answer, or a partial answer, as you'll see, we're going to have to fight off attention, because attention is going to kind of try and mess up our ability to tell where in the brain something happens. Because as soon as attention knows something, it tells it to all the brain, kind of broadcasts it, and that kind of masks any information we might hope to get. So we'll see, we'll have to fight that. We'll see that. Okay, so first of all, we'll start with the moving targets. Eye movements to moving targets are accurate. So if there's a target moving here, and you make your eyes move to it, you in fact will land pretty well on it. Now think about that. The programming to direct your eyes there is based on where it is maybe now, but it gets you to a landing spot over here. So there's a computation in your eye movement system about how to deal with that motion and get to the target. And you do it quite well. Well, how does that work? Well, you could think of correcting for the motion by just aiming ahead. Maybe your eyes are just going to aim ahead, like in skeet shooting. Did any of you do skeet shooting here? One skeet shooter. Okay, so you know you have this little target, which is a clay, it's called a clay pigeon. I don't know why I call it pigeon, but anyway, it's a clay disc, and it gets tossed up in the air and you shoot at it. And to hit the clay pigeon, you have to aim ahead of it. So that's the first thing you learn in doing skeet shooting. Here he is. Okay. It didn't need to be that loud. Whoops, turned it off. Oh. Well, I'm not sure. Okay. Anyways, well, you could do that with clay pigeons, or you could do it with cars. So you notice in both cases you had to aim ahead. Now the question is, what does our brain do? Do we do like the skeet shooter and aim ahead? Here's the clay pigeon. Do we just aim ahead into blank space when we're trying to make an eye movement to a target? Or do we maybe make up something? So here's the real case for skeet shooting, but here's what we probably actually see the clay pigeon where we're going to hit it. That's how our eye movements work. So we're going to incorporate the correction explicitly to correct for the delay. And both eye movements and perception, to keep in step with each other, do this sort of predicting the present. So you actually see things ahead of where they are, sort of moved ahead by virtue of their motion, and your eye movements do that as well. So we study this a couple of ways. This is with Stuart Anstis, you may remember. And we're going to have these two bars flash vertically, and there's going to be some motion behind them. Now the bars will never move, they just flash on and off, and they're always perpendicular and parallel. But because they flash on an edge of a moving background, they pick up the motion. We assume that they are being attributed the motion of the background. that they land on. And let's see what that does to their position. Okay, remember they're always vertical, as you see here. Then the background comes up, and I imagine you're seeing them sort of tilt in and then tilt out. Now they're tilting in and then tilting out by an awful lot, a huge amount. That red impression you're getting of that red bar over here, its top piece is many degrees visual angle away from its actual location on your retina. So your percept is not based solely on the retinal input, but is some prediction based on motion is occurring. Now, as I said, the red bar is moving. You're attributing the motion of the background to the red bar because it landed on the edge that was moving. Okay, now similar one, done again with Stewart. These are two boxes, and the one box appears as the motion moves inward, which is the one. The red one appears and then moves inward, and so that red one is pulled inward like that bars were pulled with the motion, and the blue one appears as the motion moves outward, so the blue pulls outward. Those are identical squares, and I'm going to be brave and I'm going to try and point at them. This isn't easy because my pointing is affected by it as much as my vision. But I'm going to try and point at one just to show you that they are the same. Oops, hang on. There we go. I think I have it. Okay. So they are exactly the same, but they don't look it, do they? So motion is affecting position by virtue of some kind of prediction of where it should be, where it ought to be, or where it will be in a tenth of a second. And the effects are quite large. So this has been studied for quite some time. The Niju one made maybe the most important contribution to it in 1994. You extrapolate the targets to where it will be to discount the delays, the neural delays in processing it. And the position offsets are useful. In other words, if I want to move my eyes there, I really should predict where it's going to be if it's moving. And if I want to look at it, I want my perception to match with what my eyes would do or my hands would do. And you can measure this extrapolation in the eye movement centers. If you're recording from a cell, you'll find that it responds if it's where the saccade will land. So the target's over here, and cells on this path are not responding. The cell that responds is the cell records where the saccade is supposed to go, where the target will be when your eyes land there. And this extrapolation is happening even before you make a saccade. It just happens to everything that's on the saccade representation. Okay, and you can also see it in area V4, visual cortex. Ooh, well, maybe it works. This is from Christy Sundberg, Maz Fala, and John Reynolds. You're supposed to look here, and I don't know if you can see the red in the, I don't know if we can turn the lights off, but can you see the red bars? Yeah. Okay. So the top red bar may appear to the right of the bottom red bar. And that's the effect they looked at. They placed a stimulus like this so that the receptive field was here, and they found that the response would occur as if the red bar had already moved to the center of the receptive field, even though it wasn't there yet. So the cells there were making predictive responses as well. And also with fMRI, we can get this shift seen even in early vision. So this is a first clue that we will eventually overturn. But let me describe to you a bit more what happens there. So here, the same kind of bar, and you can make fMRI measurements and find out where the response to these flashes occurs. And you find that it occurs at a retinal position, not where it actually flashes, which is totally vertical here, but either to the left or the right, as would match the percept. Okay, well, if you think about that a bit, so maybe this is making up for these delays in registering the neural responses, and so that the saccade in particular will land at the target at the right time. Well, what about if people have different saccade latencies? Some people have faster eye movements than others. What happens to them? So this is a study by L. Van Heusen and a whole bunch of the rest of us on what happens when you make saccades to this motion shifted dot. Well, it flashes once and it's gone away, but your eye movements, I say, now make an eye movement to that flash, and you'll go, in fact, to the perceived location. You'll go to where it would have been if it were moving. Anyways, that's where it goes. So the saccade goes there, And the saccade durations, the saccade latencies are different for different people. So they must have different equations of how to get to that place. If I make a fast saccade, I don't go as far ahead of the current location as someone who makes a slow saccade. So what they did, L and group, we did, was to test that as well in the perceived effect. So let's get a whole bunch of people, measure their saccade latencies. Notice that the saccades land on the target accurately, even if they have a slow saccade or a fast saccade. So they've done this prediction for different amounts of velocity, different amounts of time. And let's see how their perception is when they don't make a saccade. And in fact, so they did similar things. So you're making a saccade to the red or the green. Remember, those red and green are at the exact same location physically. And what happens is, the slower your saccades, the larger the illusion. So that really ties these predictive effects to a functional correction for the saccade itself, which can be slow or fast depending on your particular anatomy. Okay, well, this seems pretty useful. We've got this effect of motion on position, and we can use it as well to kind of break apart processes in the brain. When do different processes occur? So, for example, a square angle, you might think, okay, right angle is a basic property of shape and could be encoded as a thing. Does the motion's effect on position happen before this encoding of right angles or after? So let's ask. Notice that this bar here is landing right on a border, so it will be moved by the illusion. This bar is in the middle, so it won't be moved. And let's see what happens. Or it's a right angle, so everybody moves together. Well, remember, these are right angles. Now, does anyone see it as a right angle? No. Okay, so this tells you that this effect of motion on the position happens before the establishment of featural properties like right angles. Or here it's a letter T. There's a nice symmetry here. But keep looking in the middle, and you might see the T now as having more of a top part on the right than on the left. It seems to be skewed. So this says that the motion's effects on position happens before the properties of an object are glued together as a shape. So you might have seen something, maybe I exaggerated a bit there. You might have seen something like that. Okay, so you can use these to kind of try and ask where in the perceptual, in the visual hierarchy, this effect of motion on position happens versus various other effects, or properties, or processes in vision. It's interesting to notice that neither of these effects, well, there are other effects of position, like eye movements will shift things around, and that seems to happen after the establishment of right angles and shapes. Okay, so summary for moving targets. Large shifts are seen for perception in saccades. It's kind of a useful thing to probe visual processes. Now here's where we got to. Is a perceived location may be based on saccade location using a map format. And it's multimodal. So let me describe that a bit. So here's the map for saccades. So this is in the superior colliculus. There are a couple of other ones, but same idea. This is the fovea. This is the far periphery. This is the vertical meridian on the bottom and the vertical meridian on the top. And if I were to stimulate this point here on this map, your eyes would go right there. So we know that there's a direct link between location and activity. And if you were to look at this map when you're not making saccades, you might see 1 or 2 or 3 humps, peaks of activity. Those are sort of regions of interest. Something connects those humps to the objects they code the location of. We don't quite know how that works, but anyways, the point is, here we have sort of a map of positions for the saccades. And the idea is, well, maybe that's the map of position for everything. So our idea was that there was a common map for all modalities. Usefully, the saccade maps also respond to sound and touch. Now think about that for a moment. That's obviously necessary. You hear a sound, you want to look at it. Your saccade center has to be able to code sounds, and they do. If there's a spider walking on your foot, maybe you want to look at it, and your saccade areas need to code for locations on the body as well, and they do. Okay, so we thought we were there. This was like hubris was in the air. We thought we'd found the map, common map of location for everything. We had a whole WHERE team. This was Paris. This was Marseille. They were doing animal studies. In Dartmouth, we were doing fMRI. We're doing some TMS and EEG and some patient work. So we're doing everything, and then we had this idea, and then we did one more experiment. Okay, so although this seemed to be really promising insight about how position was coded, it's not going to be the final answer. It's part of it, but it's not the final answer because there are two fatal flaws. One is the next experiment, which I'll get to in a moment, is going to break that apart because it shows an illusion that affects perception but not saccades. So our perception location cannot be based solely on the saccade area. But also, as I mentioned before, we have to consider that attention broadcasts a percept throughout the brain. We're never going to find out where the percept emerges if, as soon as it emerges, attention then tells the rest of the brain, says, hey, pay attention here, here, here. So all the parts of the brain are kind of focusing on that area. We can't tell where this happened, especially with fMRI, which doesn't have the temporal properties to do that. Okay, so let's first of all go through this problem, that attention is a problem here. I call it attentional spoofing. The attention is kind of pretending that every part of the brain knows where the target is. Well, it's not pretending, it's telling every part of the brain where the target is. So what we're doing, what we're trying to do is find a difference between a stimulus and a percept to reveal the emergence of perception. And we're going to show how attention is making that difficult. So here's an example. Let's pretend we have an illusion where here's the physical spot, but we're going to actually see it over here. So there's a difference between the bottom-up and the percept. So we can go through the brain and look at that, right? So at the retina, of course, the physical and the neural representation is the same thing. So that's right at the retina. And maybe that's also the same at the beginning in the visual cortex. Maybe even higher in the brain. Well, here in V4, it starts to separate. So now we know we have an area where the neural response, the neural activity, has deviated from the physical in the same way that the illusion did. Maybe we have a, what do you call those things? The neural correlative consciousness thing. Maybe. And also in the frontal area, it also is. So we want to use this, okay? So that's the idea. Now, how's attention going to make this hard to do? Well, here we've got a neural correlate. It first appears here in V4. But is that really where the processing has deviated, has pushed the position away? We can find, in fact, many fMRI studies that reveal activity, not even just in V4, but in V1. So the flash grab, the one I mentioned, is in V1, can be measured in V1. The size illusion, you know, the Ebbinghaus, the discs is bigger when they're surrounded by little discs than the other one, so the Ebbing, you can find the effect of that in V1. A Mueller-Lyer, the line's longer, you can find that in V1. Memory color, if I see a gray banana, I might think it's a bit yellowish. You can find that in V1. Phantom grading, there's sort of grading up here in a mask. You you fill in the grading in the middle part. Apparent motion, some boom, boom, you seem to have some activity along the center. All of these things happen not only in V4, but in V1 if you measure them with fMRI. What's going on? So this is the attentional part that I'm mentioning, where you have to be careful, because there's a very clever experiment done in 2007 by Silva, Rees, and Heger, where they just had you trying to detect a very faint donut, okay, of activity, and you have to say yes or no, is present or not. Well, that's kind of okay, but there was a delay period, 2 seconds to 16 seconds before the target appeared, and that's where they're interested in. That's where they do the fMRI, this time period, the delay when there's nothing on the screen. And what they find is there's activity in that ring, the very same ring where the stimulus will appear if it appears. There's activity already when there's nothing on the screen. Clearly, that's attention trying to boost the activity when it does appear in the expected location. So that's telling us that attention is really broadcasting any stimulus information as soon as a percept emerges. It says, this is my target. Make sure to boost the information here. So when I find some information here, let's say I find some information here in my fMRI, I don't know whether the illusion has already emerged, whether the percept has emerged there, or whether it's just top-down attention. And most of the things I mentioned, if not all of them, were in fact top-down attention. and confounds efforts to localize. So if we really want to do this task of tracking position through the brain, we have to get attention out of the way. Okay, so that's the part about attentional spoofing. Here's an example that it is top-down attention in V1. This is the shift in position with the rotating background again. They did a nice fMRI, and they found that the angle of the fMRI activity varied depending on the background motion, as they should. But then they started to look at the different layers in V1. So V1 has like 6 layers. There's top, middle, and bottom. And what they found is it's the angle of this tilt, the illusory tilt in the activity of the fMRI was largest in the top layer. That's the layer that receives the top-down attentional input from other regions of the brain, whereas the bottom-up areas here, and these aren't very well isolated. Nevertheless, the idea is that the real activity you're getting in V1 is due to top-down attentional input. So beware, don't take any fMRI evidence of early illusory activity as being evidence that that actually happened there. It's probably a downward projection from attention. Okay. So, need better method or stimulus. And that brings us back to this one experiment, one extra experiment we did that actually torpedoed the entire description of position based in the saccade system that we had already built up. And that's this one here. It's called double drift. It's also called curveball illusion and infinite, it has a couple of different names. Anyways, if you look here, you might have the impression that this little ball is moving at an angle. But it's not. It's moving straight up and down. Okay, so something's happening because it has internal motion, and the internal motion is adding to the actual physical motion so that you get the impression that it's moving this way. So the percept is strongly tilted that way. But eye movements don't do that. So if you ask someone to make an eye movement to this target, they will go towards the physical target, not the perceived target. So really strong effect on perceived location, but no effect on eye movements. Here's the data. So here's, first of all, its control task. You make this little patch move up and down to the right here, in this case, with no internal motion. So there's no illusion. That's just the physical path. And here are the saccade endpoints. This is the physical path again. Here are the saccade endpoints, and they mirror each other. They're parallel. There's always a bit of undershoot with saccades. They never actually land on the target. They actually land a little bit before it so that they can make corrections in the same direction. But the point is that the angle is the same. Now here's the main task. You're going to make a saccade to that gabor with internal motion now. Oops, we lost that. Okay, oops. Where are we going here? That was the control. Did I go backwards? No. Oh, we lost the whole thing. Oh well. Control. Huh. Oh well, beautiful data. What can I say? Just amazing data. Some of the best. Well, I mean, it doesn't really matter. They don't have the experimental data. The experimental thing that would show that the perception is here because the internal motion is there, and the perceived angle is here, but the data are virtually identical to the control, so it's not a terrible loss of the actual one. So saccades go to the physical path, unaffected by illusion, and that tells us that perceived position cannot be based solely on the saccade location. So that whole idea of the saccades was a great idea and has lots of important points to it, but it's not the final answer. Well, we thought, wow, okay, that ruined a whole bunch of stuff. Let's try it with a monkey now. And this is a monkey with a window on its cortex, visual cortex. This is with Sandrine Cavanagh and Fredo Chavannes in Marseille. And the target's going to be moving sort of obliquely like this, and it's going to be, in one case it's going to have an illusion, in the other case is not. And let's see what the activity on the cortex does. Does V1, we're in V1 now, does V1 show any difference here? So here is the, it's also lost some text here. This should say, this is the illusion case. Okay, so this is kind of the center of the activity moving up here, that little black line, black dot. And here's the non-illusion case, the control case. So the white cross is the center. Now the two of them follow pretty much the same path, as you can see here. And if we kind of put a regression through both, it's the same, whereas the illusion is over here. So V1 absolutely does not show an illusion. This is one monkey. We thought, oh my God, this also doesn't work. So we stopped there, but then we thought a bit. We thought, well, perhaps there's no effect in V1 because this illusion doesn't work on attention. It's not only saccades are not fooled by this illusion, it's also attention is not fooled by the illusion. Well, saccades and attention are very closely linked. So some say that they're the same thing in a way. So attention is just saccades that you don't perform. So maybe we're getting this lack of effect in V1 because there was no downward projection of attention. So its attention is immune. Well, what does that mean? That means that projections were going to the physical path, and that's what we saw in this one monkey. And what does that really mean for us? That means, aha, now we can go find out where perception happens, because we won't be confused by attention's projections trying to help out, because attention for this particular illusion actually goes to where the physical target is, not to the perceived target. Okay, well, I mean, with optical imaging reflects blood oxygenation, and that's just like fMRI. The optical imaging of that patch moving across the cortex in the monkey was being detected because of the changes in blood flow, and that's what fMRI does too. So let's go do some fMRI. Okay, so we did that. It's Qing Liu and Siri Liu. And so we have the stimulus moving up and down, but appears to be drifting left, or we change the internal motion, appears to be drifting right. So that's leftward or rightward. Can we decode? So I don't know how many of you know what decoding fMRI means. It means that you present some things that are actually moving one way, well, that are this stimulus, A, and you look at all the patterns of activity in the brain, and then you present the stimulus B, and you look at all the patterns of the brain. Now you find an algorithm that maximally separates those two patterns. This says, oh, okay, this kind of activity, I always went with this guy, and this kind of activity, I always went with that guy. And you do that as best you can. And that's called the classification accuracy. And here it is. What this told us is that V1 doesn't have any difference between these two stimuli, even though the percept was strongly one way or the other. V2 and V3 may have some little bit, VMT not, but this is 60%. Let's take a look at the real stimulus. If we have the real stimulus moving on the matched angle that these ones appeared to be doing, now the classification is like, poof, no problem at all, 80, 90%, although it drops off. So these directions are extremely discriminable if they were actually being encoded as this leftward and rightward tilt. And clearly they're not. Now we did the next step, which is the most critical one. So this is one that's called cross-decoding. So we're going to train on the illusion, left and right. Remember, it's physically just going up and down, but it looks like it's left or right. So we train the classifier on left versus right for the illusion, and then we're going to have it test on the physical ones, the physically going left and right at the same angles that people had reported they saw the illusion, and vice versa. Train on the physical ones and classify the illusory ones. Okay, so trained on matched physical stimulus, so you train physical left or right, or trained on the illusory one. And test, in this case, test on the illusory one. So this angle here, the perceived angle matches that. Perceived angle matches that. So anywhere in the brain that shows a high cross-decoding is somewhere that treats these two stimuli as the same angle of motion, which they would be to you if you looked at them. Areas that don't consider them the same are not involved in perception. Okay, so successful cross-decoding indicates a common representation for the two paths, illusory and physical. Well, what do we get? Well, first of all, oh, look, there's that stray green thing. Forget that one. I want the red ones here. Look at these red ones. These red ones are the visual areas of the brain. Pretty much nothing in the visual areas of the brain show any interest in seeing these two paths as the same, even though I see that there, I see that there. One is the illusory one and the one is the physical one. They are the same, as much as can be, and yet none of the visual areas agree. Visual areas think, well, that guy was vertical. Maybe he has some funny motion. And this guy's not vertical. But the green areas are what are interested in. This is a bit challenging, unexpected. I wouldn't say disturbing, but exciting. That's better. These are frontal areas. Okay, the lateral and medial frontal areas are the ones that are particularly involved in seeing these two paths as the same. That's suggesting that their perception of position occurs outside the visual system in the frontal areas, and that requires a bit of thought. Okay. Oh, there's some other. Okay. So conscious perception of location is computed outside the visual cortex. So this has been replicated by Ho and Schwarzkopf. Well, the V1 part, the absence of activity in the visual cortex, V1, for the double drift stimulus has been replicated. Now, in the frontal area, the regions we were looking, there are no maps that we know of. So you have to say, well, how do you represent position then? I mean, we're all sort of into this map idea. Let's just have maps. But it doesn't seem to be the case that these are maps. So maybe features, maybe position is like a feature. It's like a color. You know, that object is a red object at X, Y. It's just like it's a feature. Who knows? You can make up anything you want as well. We just made that up, and we have no idea whether that will hold up as a feature, not a map. Also, we found that attention doesn't project to the expected perceived location. So attention is somehow different from perception for this particular illusion. And we'll come back to that. So attention, like saccades, may operate on a separate representation of space, independent of perceptions. Okay, so that was the idea. That was where we got to with the saccade idea in the trash. But now we have this idea that something in the frontal lobes. So clear evidence, it's when saccades are different from perception, so it can't be in the saccade area, that the frontal lobes appear to be in charge of telling you where things are. And we don't know which part of the frontal lobes, we don't know exactly what format is used or how it's done. But here's another little part, little idea to help us understand how this is organized in vision. In representing position, and something to do with frames. Okay, so we've only started this for a couple of years now, so we don't have all that much. But the idea is that scenes are hierarchies of embedded frames. Okay, so you often get the feeling this guy is moving, or this island is strangely moving. And that's because you are recovering positions relative to frames. In these cases, these frames are moving. And so we did this experiment, which we called paradoxical stabilization of relative position in moving frames. This is with Mark Oskan Stewart again, Mark Wexler, and Marius de Hart. And here's the effect. I only show a couple of versions of it, but we've done lots of different versions. There are going to be two flashes, and they're one on top of the other. And this green bar is going to show you that they're one on top of the other. And the frame is just a frame. It's just the square frame. And we can get more elaborate if you want. In the end, we want to understand that position is seen not where it just is in the world, but where it is relative to a frame. And this frame in particular is going to be moving. And you'll notice that the blue flash is on the left-hand side of the frame. The red flash will appear when it's on the right-hand side of the frame. Okay, so here's the red and the blue one. The green line shows you that they're vertically aligned. Green line's gone, boom. They appear to be very far apart. They are not. They are always still vertically aligned. I don't know if I can't do that. I need a big ruler for that. I don't see any big rulers. But you get the idea. They were like, you saw the green line. Okay. So what's happening here? So I think, I do have it the right way around. The blue flash was on the left-hand side, and the red flash was on the right side of the frame. On the screen, they're on the same location, but in terms of the frame, they're on opposite sides of the frame. One's on the left and one's on the right. And that's what you see. You see the blue on the left and the red on the right, as if there were a frame there that's kind of not seen, but it's kind of just sitting there, and you're seeing the frame relative positions of these two flashes. This is telling us that position really has many layers in terms of how do you know where things are. And one of them is, well, it depends on where that object is in its framework, in its local thing, on my desktop, on this screen, in the room, or wherever. And we happened to use a frame that was moving, and it revealed this frame structure. So we saw those two flashes in frame coordinates, where they are when they flashed, as if the frame was stationary. And we did some nice data. It doesn't matter what the speed is. The speed can be very slow. It can't be too slow. It can't be more than a second and a half or so. But it can be very fast, too, faster than your eye movements, faster than saccades. And the effect size is always the same, as if they're on the left and the right-hand side of the frame. And if I change that path length, the frame path length, from little to large, the effect is always the path length. So it's just, those data are, is this the one with 141 subjects? Yeah. So this is pretty solid data. Now, I wanted to say that a lot of experiments we do in psychophysics can have only 2 subjects. So never forget, good stuff you can do with only 2 subjects. Here we're going a bit far with 141. Okay. Now, here's just a simple example to show you how strong frames are and how trivial it is. Something, of course, so you say, oh, of course. So here this woman is going to move left and right, and her eyes are going to wink. And her 2 winking eyes are going to be exact same physical location. But you don't probably think that the 2 eyes get to overlap, but they actually do. Here you go. Okay. Now, of course, you see the 2 eyes as far apart as eyes are because you have this frame of the woman's face. The fact that the locations don't seem to quite overlap is another point about how your sort of frame is slightly stabilized. And what we do that's a bit beyond that is show that it doesn't have to have this sort of built-in framework with the whole physical structure to it. It can be just this simple red and blue flashes, which somehow get to belong to the frame because they're inside it, because they're near it, we're not quite sure. And once it belongs to the frame, then you see them in frame coordinates. And we might say, well, what's a frame? And in fact, anything that seems to be moving as a piece can be as a frame. Here's one example of something that's actually distorting a lot as it moves. But I think you'll still agree that the red and blue, even though they are vertically aligned, appear hugely apart. So these are not subtle effects. Okay. So we worked on this for a couple of years, and we were really excited about this. We did little dots. The dots move apart. But we thought, maybe we can show this to some people at a conference. And let's make it a little more interesting. So why instead of dots? We're going to do this with Governor DeSantis. This was a conference in Florida last summer. There's Governor DeSantis, who's faded from the political scene completely. No loss, maybe. And we're going to, all his body parts are lined up. We're just going to put him in a frame and show his top and bottom at separate times. You pull them apart. Or even divide them in 3. And I think we might add a little blood here. That's just Florida, Okay, and then we did, just so you know that these are not, computer-generated things, we did it with real people. So this is, I don't think you can see it, this is Viola Sturmer, a professor in Dartmouth, and the frame is going to be moving left and right. Here you are, there's the frame. Here you go, oh boy. So maybe look a little bit off. So look away, you probably see her split in 2. So now you know there's no computer trickery. But there's no pain, right? Viola, no pain. No pain, she says. Yeah. Okay. Or split left half versus right half. Remember, look to the side. So it's a very strong effect. It doesn't matter your knowledge about objects. Thank you. Should not fall apart. Doesn't seem to have any effect here. There we go. Here's Stuart Anstis himself. There's Stuart. Oh my God. Okay. So has everybody noticed that if you look right at them, there's no split? But if you look in the periphery, there is. Well, that was true in the live case because there's more light in the room that's not coming in the movie. Okay, so positions and tests are experienced relative to their position in the frame. So it's a whole other level about position. Well, how's position encoded? Not just predictively adjusted for motion, but also there's some frame involved. And this could be linked to visual stability. Imagine every time you move your eyes, the whole world is the frame, and objects remain in that frame, and that may help us understand why things are stable when our eyes move. But we don't yet know where these are implemented. We're starting some studies with animals and with fMRI. And recently, Sharif Saliki has shown that saccades, much like the double drift, saccades to the frames, to the flashes in the frames, don't seem to be affected by the frames, not as much as your perception. And so maybe this will be another attention-free way to explore how position is coded. So maybe, I just made this up, maybe you might think of frames like a frame manager on your desktop computer, that somehow your world is built up of these little local frames, and any one frame has some location in it, but if I were to move that frame around, those locations don't have to be updated, just the frame, okay? So there's some kind of frame-based understanding of the visual scene. Oh, look at that. Okay. Oh. There we go. It's a bit out of order, nevertheless. Okay, so what we were doing here is this kind of analysis across the visual cortex to find out where this happens. And we tracked the evolution of the position across the cortex. And we found that it's the frontal cortex is our main evidence, is where the position finally deviates from the physical. Now, the site of the divergence in this kind of test isn't the actual evidence that conscious perception is there. It's only that conscious perception cannot have emerged before there. It must have emerged after there. But we're already in the frontal, so there's not a lot of after left. So we're going to go with frontal is the big deal here. Well, just a side point. We said attention was independent of perception. That's a bit disturbing. We think of attention and perception as working together, and I think that 99.9% of the time they absolutely do, as they must. Just like action and perception must work together. But there are deviations, and we showed you one example, that imply that there's a separate representation for attention and for perception. And we think that attention is maybe more linked to bottom-up locations, and there's a reason for that. I mean, it tries to mimic perception for simple things in order to land on the target, but deviates for these other ones, possibly frames, because I think of attention as, again, trying to hit the targets in the early cortex. It has to know where they are. So maybe, yes, if they're moving, make that correction, but if they have these other strange things like the double drift or the frame effects, you want to ignore that. That's a perceptual effect, and make sure you get to the physical location. So I think the attention needs to reject the locations of early representation. So there are some things that it will separate from perception for, to leave the dangling participle. Okay, good. Okay, so finally, results suggest visual cortex is not part of conscious experience. We've seen that before. Of course, if you lose your visual cortex, you're not going to be conscious of anything visual. But the thing is, the processing and representations there don't seem to be the final percept. And location is instead constructed in the frontal area. So this is really just a hint. The whole perception of position, the whole position sense, is a big story that we only have a glimpse of, that it's something happening out there, and there's a lot going on, and we don't really know what it is yet. There may be some framework things like that. So this is just a rough outline. I hope to give you the idea that there's a lot of stuff to be discovered here, and the position is way more exciting than what. Go for where. Thank you.
For questions?
In the back.
Thanks, Patrick. I was going to ask about auditory saccades too, and moving targets. Auditory saccades.
Auditory saccade, absolutely.
Targets.
Cool stuff.
And if you can, like in the superior clinicus, you can give a phantom illusion where you have a visual stimulus. Vision keeps the auditory map in register. The auditory map is in register with the visual map, I should say. And if you give an auditory illusion that is counter to the visual illusion, do we know what happens?
No, I don't know an example like that. That would be quite cool. We have done auditory localization and showing how it is disrupted by saccades in the same way that visual localization is. So that was how we were tying the auditory and visual localization maps together. And we have done auditory mislocalization. If you move along and make a little click along the way, the click is mislocated. So most of the examples we have for auditory and touch, we've done also touch. You move along and there's a little buzz, and the buzz seems to be ahead of it. All of the auditory and tactile illusions appear to be similar to visual. So if you have a case where the auditory and the visual illusion are in opposite directions, that would be quite cool. I guess if you had two illusions at the same time, maybe doing opposite things, who would win? I think people have done the question of who wins between auditory and vision before.
I suspect it would be vision.
Yeah, it's usually vision. I think I remember A couple examples like that. Yeah, it's kind of like vision chauvinism. I think, I mean, the idea is that you go with the sense that has the smaller variance. It's the most reliability. I bet you could find an auditory case where audition was doing better than vision, like something behind your head, for example, and you would get an auditory dominance.
Just a question, because you kept referring to saccades, and
Yeah.
I could see when you're doing skeet shooting or playing tennis, but in the illusory motion one, it looks slow enough that I could track it with smooth pursuit. I'm wondering,
Yeah.
in your experiment, was it smooth pursuit for saccades, and would it matter?
Yeah. So, okay, so we've done 2 things on that, maybe 3. So yes, you were supposed to look here. You weren't following the orders. You're supposed to look here, and you saw this thing going like this. But you actually can easily smooth pursue it, right? And when you do smooth pursue it, there's no illusion. So the illusion depends on it having a certain size and a certain eccentricity. You make it smaller in the middle, that's fine. Big in the periphery, that's fine. So the point is, when you do smooth pursue it, you got your fovea right on it. So you got all this information about its location, and you're not going to be fooled. However, one thing we did, this was with Marvin Michler, is you take 2 of these double drift stimuli and make them go like this. And then you do the Marty Steinbach trick and ask you to track the midpoint of the 2. Okay, so now you're not looking at either. And now you will actually go on the illusory path. So unlike the saccades, the smooth pursuit does follow the perception.
I have just a story about that illusion, and it's from graduate school.
Yeah.
And Russ Develoy gave a talk, and it was basically that kind of stimulus.
Yes.
And he claimed that that was the perceptual basis of a curveball in baseball.
Oh, he was ahead of his time, yes.
Yeah, well, it was
As he always was.
a spectacular failure,
Yeah.
because this is what happened. So he explained the whole thing, and he claimed, and he showed some examples, something like that. In fact, the ball is straight, but the batter misperceives it going down.
Right.
And I don't know if you know, Gene Switkeys was in the audience, a colleague of Russ, and says, "That's really fascinating, Russ, but doesn't your theory predict that from a pitcher's point of view, or from on the television camera, where the spin's in the opposite direction, the ball would go up and away?" And Russ said, "Talk is over." Yeah. So, I'm wondering, I don't know much about that illusion, but in fact, there are certain cases where it doesn't seem to be as powerful. I'm just wondering, does it require like a really low frequency Gabor?
There are a couple of requirements there. Russ Develoy was the founder, one of the founders of this whole area with his, he used a stable Gabor, a stable patch with a texture moving in it, and it would seem to drift in the internal direction. And there were a lot of studies following his. The only thing different on that one is take that Gabor with the internal and make it move. And now the effect gets 10 times larger. The Gabor itself can't have, the pattern can't have too many stripes in it. It has to have like 3 or 4 stripes. And it can't move too fast. But within a large range of parameters, the effect is quite large, is quite big. And it's funny that I did not hear that story before, that he had mentioned the curveball.
Probably didn't repeat it to him.
He mentioned the curveball because that then became the name of the illusion when it did move by Art Shapiro, maybe 20 years after Russ had first described that effect. And Russ's effect has been studied like with monkeys and everything imaginable. It's been a very, very powerful stimulus. Yeah?
2 quick questions. One of them, you mentioned that some people think about attention as saccades not executed. What kind of data is that based on?
There's some nice articles by Ed O. and Tieran Moore that kind of summarize all of the evidence that the saccade areas are the basis of spatial attention. And they will describe activity in the spiroculicus when you're attending and not making saccades, and when you're attending to one place and not the other. So the links are very strong. I think Rizzolatti was the first to make the link between attention and eye movements. He had another name, premotor or something or other. There's lots of good evidence for it. In fact, it's hard to argue that there's anything else to to do with spatial attention that is not what saccades are programming but not doing.
And the other question, I'm really interested in when, which is the
When is cool, yes.
relationship
Yeah, yeah.
between where. And so I guess one question is temporal attention. Is there a similar association with action that's been tracked for that?
Well, temporal attention is not, it's not so well studied, and it doesn't seem to be, I mean, you can kind of say, you get to some kind of rhythm and say, okay, the test is going to be at that moment, so boom, boom, now. And so there are some studies that show that that has an effect. Yeah, and I don't really have much to say about temporal attention. There are a couple of articles on it. Kia Nobre has a couple chapters too. We did a study on temporal factors in neglect patients, and interestingly, they seem to lose temporal factors on both fields. So they have a spatial loss in the left neglected field, but temporal loss on both fields, so the bilateral loss. I can't think of much else about temporal attention. We tried to do these flash thing with bar flashes using temporal attention's cues about when it will appear, and they didn't really work out so well. So we haven't had much success with temporal attention. Others have. It's hard to know what's going on there.
I want to build on this hierarchical framework idea.
Yeah.
Have you ever played with, so you have your frame that's moving this way, but that frame can be embedded in a larger frame.
Yes.
And so theoretically, you should be able to, counteract the illusion because the middle frame is going to get mislocalized in the broader frame.
Yeah. So we have had the double frame,
Yeah.
and what happens is the inner frame rules. It's pretty much the only thing that happens is the inner frame.
So it's a local effect.
It's within, well, it's nested, so the inner frame wins. So if the outer frame is going this way, but the inner frame is going that way, you'll see offsets vertically, and you won't see a diagonal nor a left-right.
Oh, okay. Mm-hmm. So it's not like the inner frame is embedded in the outer frame.
Not for the flashed position. So the flashed position, there's two S's there, flashed positions are coded in terms of the inner frame. And the inner frame, of course, will be coded in terms of the outer frame. But that's not what you get for the flashes, yeah.
So the mislocalization has to do with this abrupt onset.
Yes, oh, absolutely. If those flashes were continuous, none of this would happen. As soon as you make the flash continuous, it groups with the whole background in the world, and that's its frame. So it's saying, like, hey, I'm static, the whole world is static, I belong to the background frame, not to this moving frame. They have to be flashed. They can flash a couple times, as long as they're not static. As long as they don't have any reason to group with another frame, to belong to another frame.
And have you ever looked at sort of ramped onsets? So instead of, because I'm just wondering about, because we know abrupt onsets have, resetting features in the cortex, a direction of attention and so on, whereas gradual onsets don't have that same kind of...
Right, I'm pretty sure if we had so we haven't done that, but I'm pretty sure if you have a gradual onset, it would have this time where it's static and the frame is moving for it to know I don't belong to this frame. It's funny to use that word, I don't belong, right? But that seems to be what perception is doing here.
Grouping effect.
It's very strong grouping effects, yeah. Yeah.
You showed sort of inconsistency between eye movement and perception. I wonder how that is related to, now Goodell's sort of where
absolutely.
Absolutely. So your eye movement, could that be analog to Goodell's visually guided action?
Right.
So
the couple of points there, that's a good point.
how do you put that perspective?
So if you know the Goodell thing is the Ebbinghaus illusion, there's this two discs, well, only one at a time, but in two discs, this one appears larger than that one because it's surrounded by little dots, this one's surrounded by big dots, and you have to go and reach it. So the reaching response has less of an illusion than perception. Now let me underline less because it still has an illusion. And Mel took that and made that the whole story of the two pathways. In the saccade, on the other hand, there's no effect in the saccade, whereas there's a huge effect in the percept. So the difference of the So it's the same story about dissociation between perception and some kind of action. But the example with this double drift is far stronger than Mel's example with the discs. But there's other issues as well, because this example only happens for saccades, for reflexive saccades. It doesn't happen for pointing. If I point, so actions like pointing get the illusion just fine.
Oh, you try that?
Yeah.
You signal the orientation, like with your hand reach?
We didn't do any signal orientation, but just go and touch the flash, the moving gabor. Touch it, and then even though the saccade would have gone to the physical location, the touch goes to the perceived location. Also, if it's a memory saccade, so the thing goes up there and goes away, and I say, okay, now move to where it was, you also show the illusion as if your memory is the perception, you're remembering the perceived location, and that's where your memory is, and your eyes move to the remembered location. So it's not an action, perception, dissociation like Mel would have liked it to be. It's a pure saccade versus everything else, perception and action with pointing. Okay, so
So
the...
you're trying to link the saccade to attention, I suppose. So you think that attention and perception is dissociable?
Attention and perception are dissociable for this, those particular illusions, only two of them so far, and we're not sure positively about the frame one, but the double drift, they are separate for double drift, yes. Attention and perception don't agree on where the target is in that case. Now you got to remember that attention is supposed to agree with perception all the time. That's its role. So there must be something else going on here, and maybe it's that attention needs to actually target the bottom-up location, and so it ignores the illusion or doesn't have the machinery to get the illusion, saying it has different machinery than perception.
Any other questions?
Voila.
Okay, just a reminder, there's a reception up in 205B. We should start shortly after we adjourn here, and if everybody needs to give Patrick